Okay, hypothesis testing. A little bit of vocab here to begin. So when we are doing hypothesis testing, it's kind of a scientific model here. So if you remember doing science fair, you did a hypothesis, and then you went through the scientific process. Similar here, we're going to have a hypothesis, and then we're going to do a statistical analysis. So let's start with our types of hypotheses. You have the null hypothesis, which is going to be a claim or a statement made about a population parameter that is assumed true. Okay, in other words, it is the status quo. Okay, and the notation for this is going to be H sub 0. So that is your null hypothesis. Okay, then you're going to have an alternative hypothesis, and that is going to be a claim or statement made about a population parameter that will be declared true only if the null hypothesis is rejected. And the notation for this is going to be H sub 1. Okay, so let's look at an example of this. We have the Ford Motor Company claims that its latest Mustang model, the 2.3 liter 4-cylinder manual 6-speed turbo, achieves 31 miles per gallon when driven on the highway. However, there have been anecdotal reports that Mustang owners are getting considerably fewer miles to the gallon when driving on the highway. Hearing these reports, a consumer advocacy group decides to conduct a hypothesis test to see if Ford's claim about the fuel efficiency of the Mustang is true, or if the Mustang actually achieves less than 31 miles per gallon on the highway. Determine the null and the alternative hypothesis for this test. So when you're determining the null in the alternative hypothesis, the best way to do this that I have found is to first find what the alternative hypothesis is, and then do the null after that. Okay, so here you say they want to know if it's true, okay, or if the Mustang actually achieves, so here we're looking at this, does it actually achieve less than 31 miles per gallon? Okay, so the null hypothesis, or sorry, the alternative, that's the alternative hypothesis. Does it actually not do what they're saying there? Okay, so we're going to say the alternative hypothesis is that the parameter, bless you, which is the mean, okay, is actually less than 31 miles per gallon. So that would be the alternative. So you start with the alternative, and then the null hypothesis is what Ford Motor Company is saying about this Mustang, is it true? That's the null, okay? So the null hypothesis then is the opposite of the alternative. So that's going to be that the mean is going to be 31 miles per gallon or greater. Okay, so we're determining those two hypotheses. You're going to look at that last sentence. That'll give you the alternative. The null is usually that initial claim. Okay, so that's going to be right here. The Ford Motor Company claims that its latest Mustang model achieves 31 miles per gallon. Okay, a couple different ways that we can test a hypothesis. Two things are always true. Okay, the null hypothesis will always include either an equal sign or a non-strict inequality sign, so less than or equal to or greater than or equal to. And then the alternative never includes any type of equality. So it's the null is either equal, less than or equal to, or greater than or equal to. Okay, if the null is equal, then the alternative is just not equal. That's so the opposite. So that's a two-tailed test. If the null is less than, the opposite of that would be greater than. And then if the null is greater than or equal to, the opposite would be less than. And then if you look there, the type of test there, when you're thinking about a normal curve, okay, you have two tail, right tail, left tail, which we'll look at in a minute here. So the language in this can get a little confusing. So when we run, so let's say we run the test and we find that the null hypothesis is false. We don't say the null hypothesis is false. We don't say the alternative hypothesis is true. Okay, we use this language here. We say we reject the null hypothesis. Okay, so we reject the null when the null hypothesis is false. Okay, the rejection region is the region where the null is rejected on the curve. So region on curve where null is rejected. Critical point, that's going to be a z or a t value that either above or below that value will cause rejection. Okay, so that is a z or t value that will cause rejection. Okay, the alpha region, that's just the rejection region. Okay, it's the area on the curve. And then a significance level is going to be the probability of making a type 1 error, which we'll look at the errors in a second. Okay, so looking at examples here, so let's say we have a hypothesis test and we want a 5%, okay, for 5% for your rejection region. The critical z-score for a one-tail test, so let's say it's a left tail, one-tail, left-tailed test. What we would do there is we're looking at this curve here, right? The left side of the curve right here, this is the rejection region. Okay, with an alpha of 0.05, that significance level of 5%. Okay, so that's our rejection region. And then this here, that's where we would not reject, or a non-rejection region. And then if this is 5%, then the non-rejection region is 95%. Okay, and that critical value, that would be, let's say we're doing a z-value, right? That's inverse norm, area of 0.05, 0, and 1, and that should give us a negative 1.645. So second distribution, inverse norm, area 0.05. It gives you a negative 1.645. Now, if we have a two-tailed test, what we would do is we would take the 0.05 and divide by 2, which would give us 0.025. Okay, then I would do inverse norm, 0.025, 0, and 1, and that should give me a negative 1.96. And it's two-tailed, so I'm going to do both sides. So I want plus and minus 1.96. Okay, so when I label this out, if I'm doing a hypothesis test, then I have two tails here. I have a negative 1.96 and a positive 1.96. Okay, now the areas to the left and right of that are your rejection regions. And then the area on the inside is your non-rejection region. Okay, and we'll do a lot of examples with that going through the whole process. But that's just starting it out, so you already kind of know how to find those z-scores. You just now are putting the label, you're going to draw it out. Then you'll run the test, and you'll see what z-value you get and then where it falls. We do have some errors that can occur. So you have a type 1 error, and that is when the null is true. Okay, so when the null is actually true, but it is rejected. And then a type 2 error is when the null is false, but it's not rejected. Okay, so let's look at that a little bit. I'll give you guys a second just to finish copying that. Okay. So type 1, type 2 errors. So consider a courtroom scenario. In the United States, defendants are considered innocent until proven guilty. This innocence can be thought of as the null hypothesis. Okay, so you're innocent until proven guilty, so innocent will be null. We'll complete the table below, and then here's the scenarios. Okay, so let's say you're innocent until proven guilty. We'll say, okay, the court can either decide that you're guilty or not guilty. Okay, and in actuality, you're either guilty or not guilty. Okay, but the court has to decide, correct? So, let's say the court decides you're guilty, and yes, you are actually guilty. Okay, well, that's correct. But let's say that you're not guilty, but you're convicted as guilty. Okay, that would be a type 1 error. Okay, so if you look down here, a type 1 error is when a truly innocent person is found guilty by the court. Okay, so the null hypothesis is true, that you're really not guilty, but the outcome is false. They say you're guilty. Okay? And then let's say you're actually guilty, but you get away with it. All right? That would be a type 2 error. Okay, the null hypothesis that you're innocent is actually false, but we didn't reject the null. Okay, we said, you know what, you're not guilty. But type 2 error, you are truly guilty, but by a court, you're found innocent. And then the last scenario is that you're not guilty and you're found not guilty. So that would be a correct scenario. Okay, let's look at another example. Hopefully this first example is not really a personal example to you, but maybe the next one might be a little bit more. Okay, suppose you graduate and land your dream job. Before you start, you got to take a drug test. All right, so what could happen, right? You either have drugs in your system or you don't. All right, so let's make the null hypothesis. We're going to assume that you don't do drugs, right? So the null hypothesis is there are no drugs in your system. Okay, the alternative hypothesis, there's going to be drugs in your system. Okay, now we're not putting a numerical value on this, we're just saying what are the errors here. But if we were going to do this numerically, it would be an equal and not equal, instead of like greater than or less than for your threshold. Because for the drug system, or actually it might be a greater than, because there's probably a threshold of drugs. Maybe, I don't know. I can only think of alcohol level right now, which is what, 0.08. So above that would be intoxicated, below that would be not. But here we're just determining the null and the type 1, type 2 errors. Okay, so a type 1 error. So type 1 error is when the null is true, but it's rejected. So the null is true that you don't have drugs in your system, but it's rejected. So that would mean the drug test came back positive. Okay, so a type 1 error would be drug test comes back positive, but you did not actually do drugs. Okay, or in other words, a false positive. A type 2 error would be the opposite. You did drugs, but your drug test came back clean. Okay, so in other words, type 1, we could say that is a false positive. Type 2, false negative. Okay, now when we do these tests, the significance of this is the significance level, like we were looking at 5%, we'll look at 5%, like 2.5%, 1%. That's the significance of a type 1 error, is what we're looking for when we do these tests. So what is the significant, or the probability, sorry, significance. The significance level gives you that probability of a false positive when you're doing a hypothesis test. Okay, so going back to constructing the test. Okay, let's look at these scenarios here, okay? So show the rejection and non-rejection region for A, B, and C below. Assume the standard deviation is known, and that is the standard deviation of a population. So we're going back to chapter 8. Remember, standard deviation of a population, that's Z. Standard deviation of a sample, that's T. Proportion, Z. Okay, so standard deviation of a population, we will use Z. Okay, so for a two-tailed test, the significance level is 0.05. It's two-tailed, so we have to take the 0.05 and divide by 2, and that would give us 0.025. Okay, then we would take, we would go to inverse norm, and I think we already did this one. This was the 1.96. And you're going to have those same significant values that we did in chapter 8, like the 1.645, 1.96, 2.33, 2.575, those similar values there. So you'll start to notice the patterns. This is 0.025, 0, and 1, and that gives us that plus and minus 1.96. So maybe that's about right here. And here. And then our rejection region would be outside of the 1.96. So if we run the test and we get a z-value of -2, we would reject. If we run a test and we get a z-value of 0.5, we would not reject. Now, again, the language is a little odd. So if we fall in the regions here that are red, we say reject. We don't say accept the null. We say fail to reject. Because you can't necessarily accept the null unless you run, accept the alternative unless you actually run another test with the alternative. So we just say fail to reject. Okay, now if we were doing a left-tailed test with a rejection region 0.01, okay, that's left, so left side of here is 0.01. So over here, 0.01. So we would just do inverse norm, 0.01, 0, and 1. So that would give us a negative 2.326. Okay, and then our rejection region would be to the left of the negative 2.326, so this would be your rejection region. Okay, and then outside of that, so anything above negative 2.326 would be fail to reject. And I like to just draw a smiley face. Okay, and then the last one is a right-tailed test. And, oh, it's over here. Okay, with an alpha of 0.02. So when you do inverse norm, you have to do area to the left here. But let's just say you forgot. Okay, and you just went ahead and you did the 0.02. Okay, you're going to get negative 2.05. Okay, but you say, oh wait, it's right-tailed, so it's just the positive value. Okay, so hopefully you notice that, but really you should be doing inverse norm area to the left, which would be 0.98, because you have 0.02 on the right. And then that would give you 2.054. So it's over here. This is 0.02. So you do 0.98, 0, and 1, and that gives you that positive 2.054 for that z value. Okay, so your rejection region would be anything greater than 2.054. The non-rejection region would be anything less than that. And again, that 0.02, that is the probability of a type 1 error. Okay. So basically, we have two ways to conduct a hypothesis test, the critical value method and the p-value method. The p-value is more widespread in the real world, but most statistics classes utilize both methods when first learning about it. For the duration of this course, it's important to learn to understand both methods since both are included on tests and homework assignments. I actually like the critical value method because I'm a visual learner. So critical value, you actually plot it on here and do it, where the p-value is just more calculations. I'm going to show you guys how to do both. These are the steps. We're going to go through the steps. So we're going to do 9.2 with the steps for this critical value here. So let me just show you these, and then I'm going to do a new video for 9.2.